Okay, so thanks for the introduction. So my job in these lectures will be to introduce you to what is nowadays called the relative Langlands program, which wasn't part of the core values volume, and indeed it was only after that it started to appear. And in some very rough sense, it gives an enhancement of the usual Langlands program to a bigger framework. And my goal, implicit goal, will be to convince you that we have some good indications now that such an enhancement exists. So let me start by fixing some notation. So I will take G to be a connected adaptive group over field K, which is either local or global. Okay. And so there are two basic objects on the automorphic side. So depending if you are working globally, then we are mainly interested, so I will denote by G, the automorphic quotient, that is the quotient of the adelic points of G by its rational points. And we are mainly interested in the representations of G of the adels that can be realized in the space of automorphic forms denoted by AG, like this, or even into the cuspidal automorphic representations that can be realized in the space of cusp forms. So this is the global automorphic picture, very roughly. And locally, we are usually interested in classifying the irreducible representation of G. So these are really, I will only work over with the field of coefficients, the complex numbers. So these are the smooth irreducible representations over C of the K points of G up to isomorphism. And so let me give some motivating examples for the relative Langlands program. So one setting we can start with is to consider a closed subgroup, H, of G. And it was often, I mean, it was realized that often what is called the automorphic period along H. So let me recall, this is a notion that already appeared in Pierre Henry's lectures. So the automorphic period along H is just a linear form on the space of cusp forms, sending phi to its integral over H. And it was realized on some examples that this kind of linear forms are often related to special cases of functoriality and or L functions. So let me give you 3 examples of such relations. So the first one goes back in some sense to Aix, at least in the setting of modular forms. It was slightly revisited by Jack and Langlands. And it says the following, so that if you take pi, the cuspidal automorphic representation of G, of GL2, and a form phi in pi, and if you integrate it over this torus, okay, and then you can even multiply by some small character, like the absolute value of A to the S, the A, then you essentially get, by some technical unfolding, an L function, which is more precisely the standard L function of pi shifted by 1/2, which is a central point here. And okay, so this is what is called an integral representation for this L function. And just one remark here is that actually this S is not really important because, I mean, from a certain point of view, we can always replace phi by its product with the determinant to the power S. And then this integral is really just the same as the integral without the power S, but for this form. And this is belonging to pi, the twist of pi by this power of the determinant, right? So we can kind of forget the parameter S here. So a second well-known example, very famous one, is due to Vaz-Puget. And it's kind of similar to the previous one, except that we replace this by another maximal torus, So more precisely, let me take L to be a quadratic extension of K. And associated to this L, we can construct an elliptic maximal torus, which is just the multiplicative group over L. And this is a maximal torus in GL2. Choose an embedding. And actually, it will be more convenient to quotient by the center, so we consider this as maximal torus of PGL2. And then, again, for pi, a cuspidal automorphic representation on PGL2, and a form phi in pi. What Valls-Piaget has shown is that the automorphic period of phi along T, when you take the square of its module, it's essentially, so again, equal to the central value of an L function. And this time, this is not the standard function of pi, but the standard function of its quadratic base change to K. So this is a quadratic base change. An automorphic representation of PGL2 over L. So it's a base change of Langlands. Okay, so these two examples give you relations between periods and L functions. Let me now give you a third example of a relation with functoriality, which has appeared in some sense in the work of Harder, Langlands, Rapoport on the Tate's conjecture for Hilbert complemental surfaces. So again, we start with a quadratic extension, L over K, as before. And we'll take, so for G, is the group GL2, but over L. And I will restrict the scalars to K in order to have all the groups defined over K. And H is just GL2, but over K, with this natural embedding in G. And what the other Langlands Rapoport noticed is that for pi, a cuspidal automorphic representation of GL2 over L, the period along H is non-zero on pi, not identically zero on pi, if and only if pi is a quadratic base change again of some automorphic representation, sigma, of a unitary group in two variables, essentially. Okay. So this gives you some examples of what the related Langlands program is about globally. So let me now discuss similar examples locally. So locally, the point is that we also notice similar phenomena. But we have to replace the period integral by the functor of H like this. So this is a functor of taking H invariant linear forms on irreducible representations, and a continuous one if you are in the Archimedean case, but let me not bother about this. And let me give you now two examples related to the last two previous ones. So there is an example 3' corresponding to the result of other Langlands Rapoport that for pi, an irreducible representation of GL2 over a quadratic extension. So everything is as before, except that all the fields are local now. This Hom space is non-zero if and only if pi is a quadratic base change, where sigma is an irreducible representation of a local unitary group this time. And so this is related to the third one. And the second one, so 2', this is the local analog of Valls-Piaget theorem, and this is due to Tunnel and Saito. So again, for pi, an irreducible representation of PGL2 over K this time. Pi supports a T invariant linear form. If and only if, so this time there is a condition not about L function, but about a local root number. So namely, you take the base change, quadratic base change of pi, and you take its local root number, and it should be +1. And so very roughly, the relative Langlands program and I will write RLP for short, is an attempt to unify this phenomena by, more precisely, by a dual picture similar to the one in the so-called, mainstream Langlands program, right? And okay, so before going into the details, let me just give you a quick partial history of the subject by just dropping for you some names.
Can I ask a question?
Yes.
What's the relationship between 2 and 2 prime? On the right-hand side, the conditions are, look different to me, so can you repeat this?
Yes, between 2 and 2 prime, yeah, it's okay. There is another result of Valls-Puget, which is, I didn't tell you what's the formula exactly, but one of the consequence of this formula is that at least if the period is non-zero on pi, then the central value of the L function is non-zero. And there is even an equivalence provided you consider some inner forms. Okay, so yeah, that's another version of the result, and that's more analog to this one, I guess. Okay, so one of the founders of the subject, in some sense, is Jacquet, who in the early 80s revisited this result of Valls-Puget by proving it in a different way using so-called relative trace formulas that you have heard about in Pierre Henry's lectures. And then there were also some investigations and conjecture by Dipendra Prasad, soon followed by work with Gross, and finally with Gann also. And this led to the so-called Gann-Gross-Prasad conjectures, which are generalizations in some sense. Or Tunnel-Saito theorem for higher rank classical groups. Okay, that I will talk about also. But at this point of the story, most of the relative Langlands program was only developed through examples. Also, we had the beginning of a general, some general machinery appearing. And it is only relatively recently, so approximately 10 years ago. Yes?
There's a lot of people. A lot more people. Right?
Yes, of course. Yeah, I said it's a quick and partial story. Yeah, of course. Yeah. I will not write all the names. These are just, yeah. I take the, yeah. So sorry for all the people. I cannot, yeah. It's roughly following also the plans I will follow in this course, and of course it's a partial history, right? A lot of other people have contributed to this, and they're just not mentioned here, I'm sorry. So, and in the work of Yanis and Venkatesh, that we saw for the first time a unified framework for that kind of questions. And this is mainly what I would like to talk about. I will also go over very important examples because the field was built using examples, and this is very important to have. And this is still under construction somehow, so having good examples is also useful to go to the next step. Okay. And so I will now start to discuss this general framework, but before doing so, let me just say one thing. It turns out it is convenient to switch the focus, not on pairs of groups GH as before, but rather to reformulate everything for G varieties, by which I mean just algebraic variety X on which a group G is acting, and my convention will be that the group is always acting on the height. And just to make the connection, very roughly, the connection with the previous setting was that if you have a pair GH, you can construct a homogeneous space G mod H. So let me now just explain. I mean, you have, okay, we are not considering, as in the Langlands program, just one group, but now we are considering group acting on a variety. And the first question will be, can we make sense of the usual objects in the Langlands program using a variety? And I'm talking more precisely about the objects on the automorphic side, that is automorphic representations and irreducible representations. And so the first question is, can we give meaningful replacement of those for varieties? And so this leads to the following question. So what is the spectrum of a variety? So I will not give an answer. I will rather give multiple non-answers and just give you some indications and of what it could mean. So it could mean many different things, actually. So the setting will be here, X is a smooth G variety. So a smooth is very, will be very convenient for me. Also, the singular case is also important, but you will hear about it in 2 weeks in Yannis' lectures. And again, there are two aspects. So either we would like to make sense. So again, it's over a K field, which is either local or global. And there are two cases. So either we would like to define a spectrum for X over K local or over K global. So let me first deal with the local case. And there we at least have two ways to define a spectrum. So there is first the smooth version, where, so this is the notion of distinction, usually called distinction, but now not for a group, but for a variety. So we'll say that an irreducible representation pi of G is X distinguished if, well, it admits a model in the space of all smooth functions on X. So you take X of K, you take the space of all smooth functions. This is naturally a representation of G of K, and you look at whether pi can be embedded there, meaning that this Hom space is non-zero. And if pi embeds, then we say it is the X distinguished. So just let me make a few remarks at this point. Is that if X is homogeneous, as in the previous case, actually this can be dualized. So pi is X distinguished because the space of smooth functions on X of K in this case is the smooth dual of the space of compactly supported smooth measures. So this is the so-called short space of measures. So compactly supported smooth measures. But anyway, soon we will restrict ourselves for simplicity to the case where xk is equipped with an invariant measure so that we can identify this just with the usual space of test functions. And another remark is that if, moreover, when you take the points of x, it's still homogeneous, then by just Frobenius reciprocity, X is pi distinguished. I mean, this is just the induced representation from H to G of the trivial representation. If and only if the trivial representation of H is a quotient of pi. Okay, so this makes the relation with the previous setting. Okay. So this is one version. And then there is another version, which turns out to be also very important because it will be, there will be a machinery behind it allowing you to construct naturally some numerical invariants, which will be important for the global picture. And this is the L2 version, where we'll say that pi is X tempered if roughly speaking, it appears in the Plancherel decomposition for the L2 space of xk, where, okay, either, again, if you have an invariant measure on xk, this is just the L2 space with respect to this measure, and it makes sense in general by taking RF densities. And this is naturally a unitary representation of G of k. Okay? And we'll say that it's X-tempered if it appears in this L2 space, so in the sense of the theory of unitary representations, meaning that it's weakly contained. So this is the technical sense in which a representation can appear in a unitary representation. And roughly, or and precisely saying that phi appears in the Plancherel decomposition for this unitary representation. But I will go back to this in the second lecture and give you more precise, explain you how you make precise sense of this. Okay? Okay, so these are at least two ways to make sense of the spectrum locally. And now I would like to speak about the global spectrum. And there again, I mean, the idea is to roughly dualize and to replace period integrals by what are called theta series. So let me explain what's a theta series. It's a very simple construction. So it's a map, theta x, from the global Schwarz space of x of the Adels, which, okay, for me here, for simplicity, would just be the space of smooth compactly supported functions. Also, sometimes it's convenient to allow the functions to be rapidly decaying rather than compactly supported at their convenient places, but let's ignore this here. And to construct from such a function automorphic function, so just a smooth function on the automorphic quotient. And this construction is like this. So you take a function f on x of the Adels, and its theta series is given by summing f over the rational points, and then multiplying on the right. So this dot denotes the variable. And of course, so g of a is acting. And this summation is invariant on the left by g of k. Right? So this is the theta series. And I would like to make just a small remark there that actually, and this was also implicit before, but I didn't talk about it, is that we need some condition in order to ensure the convergence of this. So to ensure convergence, and one very convenient one is that we can impose that x is quasi-affine, which I will also impose at some point. And why? Because it implies that x of k is discrete in the adelic points, so that this sum is locally finite. Okay, so for example, you cannot take for h the Borel. If you take for x the flag variety, you will have a problem here. And you can also check that the period is not convergent, even on cos forms. Thanks. Okay. So this is the theta series, and I didn't tell you what's the automorphic. Oh, sorry, I still have two remarks to make. One is the relation with the automorphic periods. So again, it happens when you are in the homogeneous case, right? And more precisely, if you suppose the support of f is supported only on one orbit, which must be open, of course, in X of A, then you can check it is a relatively easy exercise using that if you take a cusp form on G, and you take the theta series as before, and you pair it with phi in the sense that you take the Petersen inner product, so the L2 inner product on the automorphic quotient, you get the integral of XA of f of x, or sorry, G of A, not H of A, of f of x times the period of phi translated on the right by x. Okay? So in this sense, the theta series are essentially encoding the same informations when you pair them with cusp forms as automorphic periods. So we're not losing much information here. But one advantage of using theta series is that we can now include in the picture non-homogeneous varieties. And for example, if you take for x the affine line acted upon by the multiplicative group, then you essentially recover Tate's zeta integral, which is nice. Namely, so you take now a such function on x of A, which is just the adelic line. And I mean, an automorphic cusp form in this case is just a character of the automorphic quotient of a multiplicative group. And when you pair these two, like this, you get Tate zeta integral, which is so you pair them, it gives you this. Right? Which is just Tate zeta integral, which is of course not always convergent, so you have to assume that the real part of chi is sufficiently large, but it shows you that at least when you consider this theta series also have important meaning when you consider non-homogeneous varieties.
It's actually never convergent because you added 0 in the summation.
Right. Okay.
So
Okay. Yeah, without 0, yeah.
But you can be regularized.
Yeah. Thank you. Yeah, right. And similarly, for example, you can include in this picture the Goldman-Jacquet integrals or other kind of integrals of the same form. Okay, so let me now give you a partial answer to the original question, so at least we can make sense of the spectrum. Yes? Of the cuspidal spectrum of X. So namely, if you take pi to be cuspidal, automorphic representation of G will say that it's X distinguished if there exists a Gobo-Schwarz function f such that, well, the theta series theta f has a non-zero pairing with some cusp form in pi, or equivalently, its orthogonal projection to pi is non-zero. So we denote by this the orthogonal projection. Okay, so it gives a meaning to the spectrum, at least partially. And the idea, the naive idea, in general, to make sense of the automorphic spectrum, would be to take, so we would like to define the automorphic spectrum of X as so similar to the local setting as a support of some representation, and namely of the image of the theta series map. So let me denote it by this. But there is a problem, is that in general you cannot make this space, complete this into Hilbert or unitary representation naturally, because this would be obvious if this space was in L2, but usually it is not. So that you cannot complete to get a unitary representation. And one very rough idea to make the connection with some of the previous lectures, will be to actually still try to embed this in L2 in some sense. So it's try to define or regularize the L2 inner product of two theta series. Right. Which would at least formally give you an invariant inner form. And okay. And this is some way to formulate the relative trace formula of Jacquet that were covered in Pierre-Henri lectures. So, see Chaudoir. But I will not talk at all about this. But just to give you an idea that actually the relative trace formula might be a way to give you an answer to the question of what is the spectrum of X. Okay. So now I will, I didn't say, but my rough plan for the talks will be as follows. So lecture 1 is today. I will mostly focus on the structure, the overall structures that are behind the relative Langlands program. In particular, how you can associate to certain G varieties a dual group. Then in the second lecture tomorrow morning, I will mostly call about the local aspects of the program. And in the last lecture tomorrow afternoon, I will talk about the global aspects. So let me now enter into the technical details, so to speak. So actually, we will not consider all smooth G varieties.
Raphaël,
Yes?
did you explain or do you plan to explain why this is the same as the RTF that Chaudoir showed us?
No, I was not planning to do so. It will be in the note, maybe, but yeah. No, I didn't. Sorry. I can explain the Q&A. Yes?
Could I also ask, if you just want to define the notion of hospital spectrum of X,
Yes.
is that okay? Meaning, like, can you just do projection of theta F onto hospital spectrum and then?
No, but no. Okay. It's intersection of the spectrum of X with the cuspidal spectrum of G. The question was, is it enough to define the cuspidal spectrum of X to consider the projections of theta series to cuspidal representations? And the question is what you mean by cuspidal spectrum. So more properly, this should be the intersection of the spectrum of X with the cuspidal spectrum of G.
But I think the question of Wittek is, do we get something well defined without having to regularize or whatever?
Yes. Well, under the assumption that X is quite... Sorry. Yeah, the question was, does it always make sense to take this projection? Yes? Yes. So under the assumption that X is quasi-affine, so you have to be a bit careful about the center. So sometimes you have to consider the X modulo some central torus. But if it's quasi-affine, then it always makes sense. Of course, I didn't tell you orthogonal projection in which space. So basically L2, but sometimes you have to fix central character on part of the center. That's yes?
Would you mind explaining, so you explained already how the pairing with the theta series is the same as the P.
Yes. Yes, yes. Okay, so my first topic today is to introduce you actually to a class of varieties for which we have, or we start to have a good good conjectural answers to some of the questions that you can ask. And these are called the spherical varieties. So let me give you right away the definition, which is due to, I think, Luna and Wust, if I'm not hope I'm correct. But so the definition is I mean, very easy. So if you have a G variety, it's called spherical. If this is normal, and more importantly, any Borel B, so a priori you are over any field, so we'll take the Borel defined over the algebraic closure as an open orbit. that I will usually just denote by xb. And this is in the base change of x to k bar. Okay, so this is an absolute notion. And the first question is why this is a good category of test varieties. And I will not give you maybe not very convincing answer, but at least there is one reason, which is that these varieties satisfy certain finiteness conditions that make them easier to handle when you look at the spectrum. So basically, the spectrum will have finite multiplicities. So, and we will see in the last lecture that it's also, I mean, relatively enlightening when you look at global questions. So more precisely, so provided X is quasi-affine, which actually I will assume in one moment. So spherical, if X is normal, is equivalent to the fact that for all irreducible algebraic representation, so it's in the world of algebraic representation now, right? And you can look at the same question as before. So can you embed this irreducible algebraic representation in, can you find a model, but an algebraic model in X, that is, can you embed it in the ring of regular functions of X? And this is always of dimension at most 1. So algebraically, somehow the spectrum is multiplicity free. And there is a similar phenomenon for smooth representations. Namely, for all smooth irreducible representation of G, so assuming we have a local field now, so we look at all the embeddings of pi in a space of all smooth functions on X. This is of finite dimension, or at least it is expected to be so. So this is this is something I will discuss also tomorrow. So known in most cases, including the Archimedean case in full generality, and expected in general. So there are still some pending questions there. Okay, just a motivation for an introduction of spherical varieties, and now let me give you some examples. Because there are many spherical varieties in nature, actually. So the first main source of spherical varieties are the so-called symmetric varieties. And I should say that I will mostly talk about homogeneous varieties today and tomorrow, because somehow only the birational equivalence class of X will matter for some of the discussion. And only on the very last lecture will the non-homogeneous varieties appear or play an important role. So symmetric varieties are homogeneous varieties of the form G mod H, where H is the subgroup of fixed point for an involution on G. And these are all automatically spherical. And this includes in particular the one very important example, which is called the group case, which is where you take X to be H times, so the group G is H times H, and the subgroup is a diagonal copy of H. So you can identify, for example, by the first projection with H, and it's acted upon by G, which is H times H, as I just said, by left and right translation. Okay. And this is a very important case because we would like, naively, we would like the relative Langlands program to recover the usual Langlands program when you specialize to the group case somehow. Okay, so this is very, very rough expectation. So let me give other examples of symmetric varieties. I mean, you can take GLN mod ON. So there are two natural, or GL2N mod SP2N, obviously symmetric varieties, or SO2N mod GLN, or much smaller example is you take a special orthogonal group in n+1 variable modulo a special orthogonal group in n variable. So this is just a sphere, right? Then another source of example, which will be important for us, are the so-called overspherical varieties, which are of the form G mod S, where S contains the unipotent radical of a Borel. So for example, G mod N. Here are some other important examples. So there is GLN times GLN plus 1 mod the diagonal copy of GLN. This is called the Rankin-Selberg variety because this is related to the Rankin-Selberg theory of Jacquet, Piasecki, Shapiro, and Shalika. There's a question? Oh. And another closely looking example is this. So product of two special nocturnal groups in n and n plus one variable, modulo the diagonal copy of the small one. And this is the Gann-Gross-Brassard variety because this is, as we will see, related to the Gross-Brassard conjecture. Now let me give you a non-example, but something that we would really like to be an example of this setting, which is G mod n. So n is, again, a unipotent radical of a Borel, but on n you will put some additive character psi, which is generic. So more precisely, psi will be, so if you are in the local setting, it will be a character of n of k. If you are in the global setting, it will be automorphic character of n, so trivial on the rational points. And we'll assume it to be generic, so this is some notion that has appeared in Olivier's lectures. And okay, of course, this is not strictly speaking spherical varieties. This is just a symbol, right? But so this is not really an example. But one point I would like to make is that all the objects as defined before actually make sense for this. Namely, you can take S of x or the space of smooth functions of x. These are the functions on G which are not invariant on the left by n, but transform on the left translation by n according to this character psi. So these are spaces of Whittaker functions.
This is spherical variety, right? But it would mean
No, but I mean, G mod n is spherical, but when I write this, it does not. I mean, it's just a symbol, right? But I want just to emphasize that when you plug this x in all the constructions we had before, this makes perfect sense. So you can take all kind of space of functions, and also the construction of the theta series makes sense.
And what is it called?
Which one?
The theta series?
It's a Poincaré series? Or? Yeah, sure. And I had one last example, so. How do I do this? Come here. Okay. Okay. Okay, and the last is not an example, but it's a way to construct spherical varieties out of all ones. And it's called a parabolic induction. So there is a notion of parabolic induction for varieties. So it works like this. So if you take a parabolic subgroup with Levy decomposition LU, let's say, of G, parabolic sub, and you have a variety XL, this is L variety, what you can form is the so-called contracted product. So by definition, this is just the product modulo the action of P, where LU in P acts by the obvious way, so YG. So you multiply by the Levy part on the right of Y and on the left of G. Okay? And it turns out that if this one is spherical, this one is also spherical. It's easy to see. Exercise. And yeah. Sorry. So we'll see that actually this is an important construction because it will allow to analyze a certain important variant of X. I mean, whenever we can write it as a parabolic induction. So, any question on this? Yes.
Ask a question. So, given that this is a restrictive class of varieties, spherical, is it a reasonable question to ask for classification, and to what extent is classification available?
Yes. The question is, since it is a restricted class of varieties, is it reasonable to expect classification, and to what extent are such classification known? So I think, we have classifications of the algebraic closure, definitely, of But yeah, I will not. But yeah, there are some list of spherical varieties, including affine ones, for example. So first you have to classify the homogeneous one, and then the embeddings also. So there's a full theory, and they are classified by by some combinatorial data. But I will mention some of them now. But yeah, this will not be my main focus. But that's right. Yeah, you're right. It's a good point to emphasize that it's like for reductive groups. So we can make a list. So it's slightly more. Yeah, if you want to include non-homogeneous varieties, it's more. You have to add some combinatorial data.
There's a question on Discord about in which sense these quotients are defined
which quotient?
Whether it's PF differentiation sense. The question is in which sense the quotient is defined.
Which quotient?
All of these quotients.
I will answer.
Okay. Okay, so now I will start the bulk of the proof today, which is to describe for you some of the main structure that we can get from the spherical varieties. And at the very end, I will try to introduce the dual group, which is analog to Langlands construction for reductive groups. So the setting is the following. We'll take X. So as I said, for today and tomorrow morning, we can take X to be homogeneous, acting upon G, over a field. Everything will only depend on the base change to the algebraic closure. So let me take K to be algebraically closed. And to simplify my life, I will assume it's of characteristic 0 and spherical and quasi-affine. Because as we saw, this is a very convenient assumption. And I will also fix some notations for the group G itself. So we'll fix a Borel. And denote by N its unipotent radical as before. And A will be the canonical Cartan of G, that is the quotient of that Borel by the unipotent radical, but it does not depend up to unique isomorphism on the choice of B. And so W will be the Weil group. Then, so we have the set of all roots, phi, subset of positive roots, and delta will be the set of simple roots. And these are all included in let's say, A star, or even it's a character group of, these are in the character group of A, but I will always tensor the character group of A by Q and denote by a small A star, this resulting space. Okay, so the first invariant, one of the most basic one, but that I would like to emphasize tomorrow is actually not as well understood as we would like, is the center of X. And by definition, it's just the group of G automorphisms of X. So automorphisms commuting with the G action. And if X is homogeneous, it's easy to see that it's the normalizer of H mod H. And it's always a diagonalizable group in the spherical setting. And so in particular, the connected component is a torus. Then there is the canonical Cartan of X and not of G. So I will give some examples later. But, so we take the open, I forgot. XB is the open B orbit. So it's always affine. And we can take the quotient or GIT quotient by N. And it's acted upon naturally by A. And we denote by AX the quotients for which the action factors. So namely, this will be a torsor under the action of AX. So let me write for you another definition of AX, which will actually be important, and that I call the fundamental exact sequence. Also, it's not difficult. And it comes from considering the space of all B eigenfunctions, rational functions on X. So this is a set space of, a set or group of all rational functions on X, non-zero rational functions, such that there exists a character which I denote by chi f of B. So algebraic character of B is the same as algebraic character of A, with B acting on F multiplied by the value of this character at B. So we can now take F here and look at the associated character chi F, and it turns out that the image is the group of characters of that canonical carton AX. Right? And the kernel is, of course, the subgroup of constant functions. Yeah. So I will give one example now for AX. Which is in the group case. So we call the group case. The variety is H acted upon by two copies of H by left and right translation. So in this case, the canonical cartan of G is just the product of two copies of the canonical cartan of H. Let me denote it just for now as AH, and not to be confused with the split center. And AX is a quotient, and it turns out that AX can be identified with AH itself, which is good news because we would like to recover the canonical cartan of H. But the map here is not like just a product; it's slightly twisted. So it sends A1, A2 to A1, and yeah. Where WL denotes the longest element in the val group.
Can you pull down the middle word?
Yeah, sorry. Pull like this. Wait. Okay. Now a third invariant, which is called parabolic type. Okay, for the moment, these are the easy invariants. So this is defined, the definition is parabolic subgroup, and this is a stabilizer of the open B orbit. So it contains B, it's a parabolic subgroup, and roughly, very roughly, but we'll explain more tomorrow, it controls the size of irreducible representations in the spectrum. But for the moment, let's just say that the bigger, H, the bigger Px. So the smaller x, the bigger Px is. So let me give you two examples. So Px is B for H small. And there are many examples. Actually, most examples I gave before of Px equals to B. But let me just give one example, which is JLN.ON. So ON is actually exactly of the minimal size possible for a spherical subgroup. And another example where Px is not B is that for X, now we take GL2N, what SP2N. So SP2N is much bigger than the orthogonal group O2N. Px is the standard parabolic of type 2222. Okay. Okay. And just terminology, we say that X is tempered, and I will explain why tomorrow, if this parabolic is equal to B. Okay, so now we are coming to the most subtle and some of the most important invariant. And okay. okay, we'll see here, which is the Weil group. So, and this is really the starting point. I mean, where we'll see coming a root system. So, and this was originally defined by, by Brion, I think. But the definition I will present here is due to Knop. And okay. So one notation. So we have this A star I defined before, and we can define the same for AX. And since AX is a quotient of A, AX star embeds naturally in A star. And very roughly, so to put it in a nutshell, WX is a certain subgroup of the normalizer in the Weil group of this subspace, such that, so the definition of Knop is kind of analog to the definition of the Weil group you can get from Chevalier's theorem. Namely, it's describing the ring of invariant functions on some space in terms of this Weil group. And more precisely, you have to consider the cotangent bundle of X. And if you take the quotient, so this is GIT quotient, I will say what it is in one moment, is the same as the quotient of AX star by WX. So this is very rough. I will give more details in one moment. And this GIT quotient, so the point is that, okay, GIT quotient usually is spec of, yeah. But remark that T star of X is homogeneous and can be described as the orthogonal comp of H in G star. The dual of the Lie algebra of G times, contracted product with G over H. And this can be described now as this, which is just the spec of this one. Okay, so let me give slightly more detail, maybe right here. So more precisely, I will not go much into the details, but I will just try to write a diagram explaining the definition. So we have, I should start here, I think. The cotangent bundle, and then it goes to the GIT quotient. And as I just said, this should be identified with AX star mod the Weil group. But this should be compatible with other maps, right? So first we have a natural map here to G star, which is called the moment map, and which is dual to the natural map you get by differentiating the action, which is from the Lie algebra of G to the space of vector fields. Okay. And then G star you can map to its GIT quotient by G, which according to Chevalier's theorem is just the GIT quotient of A star by the Weil group. This is Chevalier. And we would like to have an arrow here making the diagram commutative. So this is one first thing, but it doesn't tell you exactly what is WX still, up to conjugacy, for example, by this normalizer. So to make a very precise definition, you have to go up a little bit and define what Knop called polarized cotangent bundles, where you take the fiber product over the Chevalier quotient with A star. So this one is going to A star, and there is an actual action of the Weil group. And Knop has defined a canonical, using X, irreducible component.
Raphaël?
Yes?
There is an A star which is a dual Lie algebra, and there's an A star which is character group tensored by Q.
Yes. Yes, that's right.
So
okay.
when you consider the moment map,
Yes, sorry.
you mean A star, the dual.
Yeah. I have to.
Yeah, maybe over F.
No, but okay. K is of character 0, so it contains Q, and I can tensor everything to Q.
K is
Yeah.
0 and the bracket closed here, right?
Yeah, but it's of characteristic 0, so I can base change to K.
Yeah.
Yeah, so you have to base change to K, yeah, right. Everything is in the dual of the Lie algebra, you're right. And so that's a certain irreducible component which turns out to map to AX star, and such that the stabilizer for this Weyl group action is actually the Weyl group semi-direct product with the Weyl group of the parabolic Px. And this map this map is descending from this one. Okay, this is the definition in one. Yeah, I will not say more about it. But there is a Weyl group, which is, and you can take this as a rough definition. Okay. So now that we have the Weyl group, we would like to define a root system, of course. Ah, yeah, I should give some examples. Sorry. So, as always, we first look at the group case. And in this case, as you may expect, WH is the same as the Weyl group of H. And it embeds in the Weyl group of G, which is WH times WH, in a diagonal way. So there's no twisting there. Other examples are the Rankin-Selberg or Gross-Spherical varieties, where actually the Weyl group of X is the same as the Weyl group of G. And finally, one last example, so where the Weyl group is very small. So we'll take SO2n plus 1 mod SO2n. So this is the sphere example, where WX is just Z mod 2, and it embeds into W by sending, this is just a subgroup generated by one reflection along the longest positive route.
Does it make sense to say what AX star is in those cases?
I will in one moment. Yeah, I was planning to say more things when I define the dual group actually.
Is there some general formalism that gives that each of these X are actually quasi-affine?
What?
Is there some general principle that says these X are actually quasi-affine?
No, I am assuming that these are quasi-affine. And there are examples where those are not quasi-affine. So take the flag variety, for example.
But I'm saying literally the quotients on the board. Like, is that a computation that is quasi-affine?
No, yeah, sorry, yeah, I didn't say it. But when you take the quotient by a reductive subgroup, it's always affine. Yeah. It's a theorem of, yeah, this is if and only if. Right. Okay, my last topic about general structure are the spherical roots. So now that you have the Weyl group, you would like to define a root system. And, okay. Turns out that this WX is the Weyl group of a root system. So let me give you a possible definition of that root system. So you start with the valuation cone, V, which is, so the set of all Q-valued valuations which are G invariant and trivial on K star. And by the, it's still there. So by the fundamental exact sequence, which is here, just there, by restricting these valuations to the group of B eigenfunctions, you can map this to, so this is restriction to KXB. You get an element of what I would denote, so the dual of AX star, so AX. And it turns out that this is always injective. And here's the point. So this is a fact proved by Brion and then reproved by Knopp, that AX minus, which is the image of this valuation cone, is actually a finitely generated cone and a fundamental domain for the action of the Val group. And this implies actually that Wx is the Val group of a root system with some system of simple roots. I mean, this will be the Weyl chamber. So if you want the simple roots, you have to take the generators of the extremal rays of the dual cone. And the dual cone, so I think this was the notation used in Pierre-Henri lectures. So the plus is on the left. So now this is a root cone. And okay. So this is a set of chi in AX star which are negative on AX minus. But there are more than one way to normalize the simple roots. Of course, we can all scale them, for example. And so this is a set of simple roots that I would call delta x. And so there are various normalizations possible, but we'll use one which is turns out to be the one which is the more meaningful for the representation theoretic point of view, which, yes?
If I have never thought about G invariant valuation.
Yeah, we'll say, if I have time, we'll say something about it. But yeah, roughly speaking, valuations are, you should think as valuations associated to devices, for example. And these are valuations associated to devices that are not existing in X, since X is homogeneous. So this is a kind of replacement of a way to look at the X, I mean, intrinsic way to look at the geometry of X at infinity, by talking about the valuations of devices at infinity without constructing them. So, but yeah, if I have time at the end, I will explain why this Weyl chamber is also related to the geometry of X at infinity. So the normalization we'll use is this one, and it's used to Sakaladis and Venkatesh. This is not the usual one in literature on spherical varieties, but we may take delta x consisting of primitive elements in the root lattice for G. So this is the lattice generated by the simple roots for G. And of course, there's only one generator for each extremal ray, which is primitive in this root lattice. And it turns out that these are the simple roots of a root system. And we'll take those. And OK, let me just write one position. It turns out that these simple roots are not very far from simple roots of G. So no, I will write on another board. And I will also explain why this normalization is natural. Ah, yes, sorry. Like this. So, opposition for, if you take, so these are called the spherical roots. Unlike, I mean, these are not called the simple spherical roots, but spherical roots means always simple roots. So if you take a spherical roots alpha, so there are two cases. So one, alpha is already a positive root for G, or alpha is a sum of two positive roots. So where gamma 1 and gamma 2 are positive, And actually, in this case, the decomposition is not unique. But if you impose, moreover, that these two roots are strongly orthogonal, in the sense that the only roots in their span are plus or minus gamma 1 and plus or minus gamma 2, then these are unique. And now, here is why this normalization is natural. So when you have simple roots, you have simple co-roots. And simple co-roots are characters of the dual group. So let me dualize my two cartan. I will give one just after, in the group case. So we can dualize the two cartan at first. So it gives you a dual tori over C. Okay. And so the co-roots of for alpha are characters of this dual torus. And let me write here. So in this case, this is alpha check. It's just the restriction of gamma check to AX hat. And in this case, alpha check is just the restriction of either gamma 1 or gamma 2. Turns out that these are the same to AX check. And so in particular, you remark that delta X check, so the set of spherical co-roots, is always included in the restriction of the co-roots of G to AX hat. And we'll see in one moment why it is important from the dual picture, but this is the unique normalization of the spherical roots with that property. And now I give an example. So again, the group case. Right. So recall that AX is just AH, seen as a quotient of AH times AH in this slightly twisted way. Then delta X turns out to consist only of roots of this form. And these are more precisely sum of two roots where alpha runs over all the simple roots of H, and you have one copy of alpha for the first copy of H and a second copy of alpha for the second copy of H. Right? So in particular, this is naturally the bijection of delta H, and we recover the root system of H. Okay. And another example is, of course, if the Weil group of X is the Weil group of G, which was the case, for example, for the Rankin-Selberg of Gauss-Parseval variety, then the spherical roots are simply all the simple roots of G, so that it is the same root system as for G. And yeah, last example is you take X equals PGL2 mod the normalizer of a maximal torus. Then, I mean, the Weil group is the same, so delta X equals delta, and this is just one root, alpha. But the character group of AX, in this case, AX is A mod plus or minus 1. And so it's generated by 2 alpha. So we see that.
So in the first example, you write alpha 1 plus alpha 2.
Yes, I mean, in this case, G is H times H. So it's just that every simple root of H will give you 2 simple roots of G, so either one in the first copy and one in the second copy. And these are the meaning of this. Okay. So, I will talk about it later. Not for the moment. No, you are right. No, we don't. No. It's fine. I think it's fine. I think it's later that we have to twist. I mean, Chevalier involution is preserving the pinning, so it's preserving the cycle groups, right? So I think it's fine. No, it's not. Yeah, it is right. No, you're right. Yeah. No, okay, thanks. So I made a mistake actually.
Maybe you say what AX star actually is to clarify. A good case. So it's not a diagonal.
Yeah, yes. I will do this. So let me correct what I wrote above. So in the group case, now what you get is not alpha 1 plus alpha 2, alpha 1 plus W minus WL alpha 2. Sorry. So where WL again is the longest element in the Val group. Oh, you're right. And this is because in this case, so as we saw, the quotient of A to AX is slightly twisted, but you can look to the dual picture. So and it's sending an element A here to A WL of A inverse, which is exactly the dual of the projection we had before. Yeah, thank you. Okay, so last topic today, because I will not have time to talk about anything else. What?
Third example,
Yes.
we took NA instead of the torus. Was there some reason for it?
Yeah, it's because in this case the character group of AX is smaller because AX you have to quotient by this plus minus 1. Whereas if you just take the torus, then AX is A and is generated by alpha. The character group is generated by alpha, but here it's really generated by 2 alpha. So you see that the root is not in the weight space. So it's yeah. Was it? So, okay, now we would like to define a dual group. So the idea is to do it in a combinatorial way, much in the same way as Langlands defined the dual group for a reductive group originally. So you start, I mean, now you have a base root datum, right? Essentially, so. And you like just to exchange the roots and the co-roots, and to define the dual group of X to be a dual connected reductive group of a C with that as a base root datum, right? But the problem is, and you can already see it on this example above for PGL2 model normalizer, is that there might exist some alpha in delta X such that when you intersect the weight lattice with the line generated by alpha, you only get the line generated by 2 alpha. So sometimes alpha is not in the weight lattice, and then it is not really a base root datum. So, and these are called roots of type n. And really, anything that I'm going to say only works when there is no roots of type n.
So that's the basic example.
And that's the basic example. Okay, so if no roots of type n, PGL2 mod normalizer of the torus, yeah, so it's a basic example of a root of type n. Okay, I just write. Yeah, we start at 7. So, so now if there is no root of type n, we define the dual group X hat as a connected adductive group of a C, such that, I mean, equipped with an isomorphism of its base root datum with the dual base root datum here. And the point is now, I mean, this is not the end of the story, because as I already explained, there is a natural morphism between the dual Cartan, and this is the maximal torus in X hat, this is maximal torus in G hat. Turns out that Px will also give you a maximal certain morphism of SL2 in dual Levy, standard Levy in the dual group. This is principal SL2 in this dual Levy, which is given by the canonical pinning of G check, and that these two morphisms commute. So you get at least a morphism from this product to G hat. And I will end with this. So then Sakellarides Venkatesh have proposed some precise conjecture of how to extend it to morphism from the full dual group of X to the dual group of G. And this was proved by Knopp and Schalke. This extends to morphisms that we know by iota X. With one condition, which is that it should send the root space associated to alpha, where alpha is a spherical root, to the sum of the corresponding root spaces for the co-roots associated to the roots. I mean, you write as before alpha as a sum of 1 or 2 positive roots, and this gives you some root spaces in G hat, and this is the condition which prescribes this morphism up to A hat conjugacy. And last but not least, I will just say it orally. Actually, slightly after this paper, Knopp came with a stronger condition telling you exactly where this root space of X hat should go in G hat that are natural from some, if you want, some functorial properties of the dual group. And these conditions give you the morphism, a characterized morphism uniquely up to AX conjugacy. And this in particular lead to L group, because if you have everything is defined of a K, you can show that this notion is stable by pin automorphisms fixing everything. And so you get a morphism like this. Okay. And next time I will explain how we can use this to predict some stuff, and we'll end by just this. This is a table of examples. And right, and just mention the first case is the group case, and as you see before, this was already visible on the morphism between maximal tori. Is that the morphism the L group of X is of course the L group of H, the usual one, but L group of G is a product of two dual group of the gamma. Sorry. But the morphism is not the usual, the obvious one, which is diagonal. It's twisted by a certain evolution, which is called the Chevalier morphism. Thank you. Let's stop here.
Thank you.